likely this is an uninitialized variable situation. The next step is to find out who is supposed to initialize this variable. And to do this, we're going to make a copy of crash HTML, or we'll call it safe HTML. We're going to edit it, and instead of a checkbox, we're going to use a text input field. Now, we know that the create text range function is supposed to be called on text fields, so this should work fine without causing any problems. We shouldn't see any crashes. Then we're going to restart Internet Explorer. Sorry, we're going to start Internet Explorer again, and this time we'll pass safe HTML to it. We still have our breakpoint in the run function, which allocates the variable. We run it, it hits twice. The second time is the one we want. Let's put a write breakpoint on it again and find out who writes to it. So here's our structure again. And you'll notice that the contents of that structure are actually the same every time. So apparently when we start Internet Explorer this way, it is deterministic. So we get the exact same behavior and the exact same memory layout every time. Let's put a write breakpoint there. Find out who writes to it. Let it run. And our breakpoint hits. And it hits in the cinput create text range function in MS-HTML. And in retrospect, it's kind of obvious that when you call the create text range function on an input element, then this would translate to a C++ call of create text range in the cinput class. But I didn't know that at the time. If we look at, we'll copy that address and then we'll look at it in IDA again. Okay, so here's the location where we initialize the variant structure. And if we take a look at the create text range function, we're somewhere inside it. And here's the beginning of the function. The easiest way to debug this is to put a breakpoint in the beginning of the function, then just see what happens. So we're going to restart IE again. And we're still running the safe HTML file. We don't need any of these breakpoints. We'll put a breakpoint in the beginning of create text range, let it run. So create text range executes. We're going to step through it, and we'll see how it establishes the stack frame. Then this is a check for one of its arguments being null. We pass that. Then there's another check for a bit field in the current object, and we check if bit 20 is set, and we also pass that, and then we continue, and then we call some functions, and then eventually we get to the initialization code. So now let's redo this again using the crash HTML file and see what the difference is. Okay. So this time we load crash HTML. We still have our breakpoint in create text range. Yes. We let it run. If we step through it, we want to find where the two paths diverge. We want to find what the difference is. And if we had something like binnavi, this would be very simple, but we can do it in WinDBG2 manually. So first we go through the function prolog. Nothing interesting here. Then we do this check for the argument being null. We pass that again. Then we do the check for the bit field. We look at bit number 20. And now the branch is taken. So apparently this bit was set here, and it was not set when we opened the safe HTML file. And this leads us to a call to set to the setErrorInfo function. Let's take a look at the function in IDA. So here's the function prologue. Here's the check for arg4 being null. And if it is null, then we move this constant into EDI. And this constant is one of the standard Windows return codes. It's einvalidArg. And then we jump to this location here. And at this location, we call setErrorInfo, which sets the last error code, and then the function returns. So we're going to call this location setErrorAndReturn. Okay. The argument to setErrorInfo, which is the error code, comes from the EDI register. The EDI register was just initialized, it was just set to the einvalidArg return code. So apparently, if the argument is null, we return that error code because the argument is not supposed to be null. However, in both cases, safe HTML and crash HTML, we passed through this check, and we got to the second check here. That's a test for bit number 20 in this field in the object. And if that check fails, we jump directly to setErrorAndReturn. And you can see the difference between these two cases. Here we initialize, on this path, we initialize the invalidArg. We initialize the return code and set it to einvalidArg. On this path, we don't. So when we call setErrorInfo, we're going to set the last error code to EDI, but EDI was set to 0, and we never changed it. So the vulnerability is a result of a missing assignment to EDI on this path. Because we don't set the error code, the program leaves it as 0. So the function aborts its execution, it exits, but the error code is still set to 0. What happens in the caller, and with a little bit more investigation we can confirm that, what happens in the caller is the caller looks at the error code to tell whether the function succeeded or failed, and since the error code is 0, it thinks that the createTextRange function succeeded. If it when it normally succeeds, it initializes that variant structure. In this case, the variant structure was left uninitialized because the function bailed out in the beginning. But the caller doesn't know that. So the caller will later try to use the variant structure that was supposed to be initialized here. So it's a miscommunication between the two functions. This function should return the proper error code. So now that we know what the problem is, we can try to fix it. And right now we're stopped right before the call to setErrorInfo. If we look at the ESP register, if we look at this is the stack, the last thing on the stack will be the argument to setErrorInfo, and it's 0. So we're going to replace it with 8070057, which is the einvalidArg constant. And you can tell that I've done this before because I don't really remember Windows error constants off the top of my head. So now we have the error code on the stack as an argument. And if we let the program continue, we don't get a crash. Amazing. Instead, we get a little error message here. And let's open it. We get an invalid argument error on this line in the JavaScript code. So apparently the error code that we return gets propagated all the way up to the browser, and the browser displays it. And this seems like a pretty decent remediation because it is, in fact, an invalid call to execute this function on a checkbox. So this seems reasonable. So we know how to do it by modifying the stack, but now we want to do a real hot patch where we actually modify the code so we don't have to intercept the execution every time. To do this, I'm going to open the opcode bytes here. I'm going to show. So these are the actual bytes of the program. So as I said earlier, the problem is that after this test instruction, we jump straight to the set error and return location instead of initializing EDI. It would be great if we could add a instruction here to set EDI, but unfortunately we cannot move the two instructions apart and insert stuff between them. So instead, we're going to change the target of this jump instruction, and we're going to make it jump back up here to the move EDI invalid arg instruction. So if we do that, after the test fails, we'll go back up here, we'll set the error code, and then we'll go back to set error and return, and it should work. If we look at the two opcodes of the function, 74 is the opcode, and 7F is the address that we want to jump to. This address is the difference between the target address. This offset is the difference between the target address and the current EIP. So if we want to calculate, the new offset, we should subtract. Or was it the other way? We will subtract the EIP. Okay, it was the other way. Subtract the other thing. So we subtract the current EIP from the target address, and we get ED. So if we replace the second byte with ED, our instruction should jump to the right place. So let's try that. I'll remove all breakpoints. I will go to this memory location. Here we see the 747F bytes. I replace it with ED. And now to confirm that everything is fine, I will unassemble the code in memory, and we see that this jump now jumps to C277, which is up here, where we set EDI to, where we put the return code into EDI. So everything seems fine. I'll clear the breakpoints again, and I will run Internet Explorer. And now we can refresh this. I'm clicking the mouse, by the way. We can refresh this as many times as we want, and Internet Explorer does not crash. So if you actually want to turn this into a real hot patch, which can be deployed on a user system, it's just a simple exercise in C programming. You need to load your DLL, you need to find that location, change that byte, and you're done. What? Oh, because Internet Explorer has this thing where it only shows you the first error, and then it hides the second ones. It's an option you can set in the settings. It's to prevent scaring the users by showing them error messages. So that's the end of the demo. And now, before we finish, I want to say thanks to a few people. Rolf Rawls from Saber Security for doing a great job on BinDev, which I use